Alrighty then. It says we're live. We clap, even though the AirPods kind of get it. Oh my god, my hair. Ah, recombobulating me. But other than that, hey guys, what's going on? So yes, as we have our board from the other day still up here. We're going to let folks start to join us from all the different places on the internet, the YouTubes, the X Twitters, the Blue Skies, wherever from whence you may come to this broadcast or temporally in the future. Welcome. We're going to be doing some rampant okay. We're going to be doing some rampant speculation, but all at the same time, it's like, wait a second. You come across different stuff and things, and you start to look at some of the numbers. And again, as we had previously done at some point, maybe it was the one. No, I think it was the one before the last one. We were talking about how to do magic on Wolfram Alpha. Yes, that modern computational tool. A project so crazy that even its creator, Stephen Wolfram, had to keep secret from some members of his management because he was afraid they would talk him out of it because it was an idea so crazy. All I know is it basically gives you magnitudes of the Library of Alexandria in computational fashion. That's, yes, I'm a Wolfram fanboy. That's fine. But today we're going to be talking about why does C squared seem to pop up in so many places? C squared, what is that? I don't know. Something music, symbology and everything, or, and in the realm of physics, typically, because we never use the same notation for multiple things. C is the speed of light. It is the maximum speed within most regimes as we physics as we know it. Okay. So C squared, we may recognize from our whole E equals MC squared and all that jazz. And I should probably actually erase or letting folks get in here because I'm gonna spend the time to put up a board, talk about things. I should probably actually utilize it rather than just keeping all the same old stuff back back where it usually is. Yes, I know. Yes, scheduling on stuff and things. Wait a second, is he in the mountains? Is he on the coast? Where is he? The algorithm don't know what to do with it. It's okay though. It's okay. We'll make our way through this different stuff and things. It's interesting where one may happen to get different viewers from, and again, I understand some folks are just passing through. Some folks are like, why the heck did this algorithm bring me here? I cannot answer that. It's it seems to be getting constant feedback from us. Yes, I'll finish in about the next minute, and I'll get to any folks that may happen to be in the chat because we do like to have interactive things. I realize I'm terrible at that, but I figured that as long as I'm consistently terrible, whether it's 10, 100, or 1,000, if I'm consistently bad, uh, eventually maybe I'll get better. I don't know. I think it was Tom Bellew who said something like that. It's like, well, if you can't see yourself doing this, become the person you want to be to see that. I did like that. I'm not sure if I could promote that to other folks. I feel like a lot of stuff is uh, personal in that respect. And everyone loves to buy, nobody likes to be sold. I actually learned that from an online sales training course, which that was the most powerful line in the whole thing. It's like, you could say this, you could say this. It's like, listen, everyone wants to buy, nobody likes to be sold. Once you understand that concept, I'm like, all right, a lot of things make more sense. So I ain't here to lecture at somebody to tell them how to do stuff in their life. No, I'm just highlighting some very interesting things that at least I don't understand. Probably some folks out there. Actually, I know there's folks out there that understand these things far better than I do. Wow, it really does just like move the stuff around. Just going along and like, oh, there's accumulation. Here we go. We'll move it down to the edges of the board. There we go. I think it's one of those things where you should probably actually clean it once in a while. All right, it's the new board. Let's see, where are we at? Okay. So most of the time, I'll use one of our new markers. We have our standard C, C, which is equal to the speed of light. in a vacuum. We need to put that in there. In a vacuum. Gonna put quotations around vacuum because there's no true vacuum, at least as far as we understand it. All right. Speed of light in a vacuum slash medium. Okay. We've got that thing. All right. So I want to see c squared. Well, c squared equals the speed of light squared. Ah. Or it's equal to, let's go to the class. Boom. Don't worry. We won't go too crazy. Okay. Maybe we'll go a little crazy. It's all in good fun. Let's just do this. C squared is times 10 to the 16. It's 10 to the 8. All right. Notice these numbers. Yes, Rick. Temporally catching up. Okay, so we got our 8.988 times 10 to the 16 meters per second. All right. So it's speed squared. So that's 8.9. 88 times 10 to 16 meters squared seconds. Meters squared over seconds squared. All right. That's cool. It seems to be fat, but it's really fat. It seems to be squared. It's an area acceleration. Oh, that's actually a very interesting words that come out of my mouth. Because we got the second derivative of time. Sorry. All right. We got seconds squared. Okay. All right. That's groovy. So why am I showing you this? All right. So Rick is here, and Rick has pointed out looking at things inversely can be very, very interesting. So what happens if we do this? As we do 1 over c squared. Going to equal a slightly different number, but a number that okay. I actually remember it. 1.11. We're going to round up. Actually, to be fair, we'll just put it as it is. To how precise would I want? Okay. There's not actually a 3. You know what? I'm just going to leave it off because I'm going to argue about it. 1.11 times 10 to the minus 17. And this would be seconds squared over meters. Okay. Squared. There we go. All right. All right. I'm just going to put the 3 there. I'm going to put the 3. It's not 3. It's actually like 265. It's going to bother me. It's going to bother me. 1, 2, 6. There we go. Okay. Yes. All right. We're synced back up. All right. So let me actually. All right. So we're going to do this. We're just going to invert this. And it'll zoom up a little bit. All right. So what the heck are we looking at? No, we want it as a unit. There we go. All right. Let's make it so I can actually see. Oh, wait. I'm not even. That was terrible. I wasn't even sharing the correct thing. There we go. All right. The 1 over c squared, that's the thing I'm showing you. That's the wrong number. That's the 3. Hold on. More digits. There we go. Okay. See, now I'm happy. All right. So the whole thing is the speed of light conversion factor for c squared. If we do 1 over it, you get this number, 1.1126. Well, it's 10 to the minus 17 kilograms per joule. That's mass per energy. I can tell that because it says mass per energy. All right. Why am I showing you this? We've done this before. Occasionally, you got some questions. At least I know I do. When I got a question, I'm like, I should think about this. So, all right, if we've conjectured and I'm a crazy person, I'm gonna throw a conjecture out there, something like, I don't know, what is What is we're gonna say? Well, we're gonna claim the size of radius of universe as a thing. All right. Well, let's do a thing. What thing can we do? I don't know. Let's do something like this. Let's do meters squared over blank length because it's a conjecture, so we can do that. All right. So that would give us a really ginormous radius. Let me say a really large number. Well, 6 times 10 to the 34 meters. That's really ginormous. Now, again, I hear folks talking about inflation. Maybe that's a thing. Maybe it's not a thing. But I'm just like, well, let's just ask a logical question. We're going to have some form of something expanding from maybe a really small point, so maybe say a singular point. I'm thinking more along the lines of like, I don't know about the 10 to the Planck length times meter squared or something like that. Just hypothetically. Um, okay, how long would it take to get from a really, really tiny, small thing to its state? I don't know. Well, if there's a maximum speed, let's say hypothetically c, the speed of light, how long would that take? It'll take 2 times 10 to the 26 seconds. Well, that's almost a billion seconds. What's that? Oh, it's about 10 to the 18 years. So that's about 100 million times longer than the currently established uh, yeah, age of the universe. Because we got like the 13.8 giga years or billion years, if you want to sound fancy. And that's like 100 million times more than that. So I mean, that lines up with the other magnitudes of stuff. What's going on, Fatal? How you doing, my man? Keep on listen, if you get a chance to watch Ultraman Towards the Future, Ultraman great. I'm just saying it, it's only like one season. It's I think it's easier to get into it. I did like Jack Shindo and stuff. Or uh I'm not a doctor, man. I can't answer that question. I just I listen, I took like a 6 month break. I'm getting back into it. I was just it does feel good. Hey, you do what you can. Tallest monster of the stone. It might not be geologically correct, but sounds pretty good. Okay. All right. So we've got we've got this whole number here. So I'm like, all right, in order for it to get to a tiny little thing, some say maybe say a primordial atom. Those quantum fluctuations that are waving our hand kind of like a wizard. So we're gonna say, oh, this is a tiny little thing. Say it's maybe about, I don't know, the electron's compton radius, approximately something like that. So a really tiny thing. In order for it to get to that ginormous radius, it's gonna take about 100 million times longer than the estimated age of the universe currently. I mean, that lines up with the other magnitudes. So, what would that mean? It would mean if there was something to this universe as we know it, small u, um, it's probably a lot older than we may suspect. Now, that may explain a lot more things, but that's not why we're here. That's not why we had that C squared. Click Brady. Uh Fatal. I'm just saying I was dropped on my head a number of times with myself and other folks. I can't comment on that. Uh, I'm just saying if one is going to join a monastery and actually try to do things, I should probably actually try to do things. Um, Hyperbolic time chamber. That's just what I think of it as. You just use it with your mind. It's kind of like when Gohan and Krillin and Piccolo, they're doing the meditation thing. You just having time to think can make a big difference. Uh, Depends on what you focus on. All right, so we're gonna bracket this, and all right, here's a crazy thing. Hold on, where am I trying to bring this crazy thing? Ah, yes. Okay, so the crazy thing was I looked at this. I'm like, well, does this have anything to do with, I don't know? It's like a lot of seconds. Well, what if I related it to something I know? How how would okay? We've got meter squared versus the Planck length. What has time got to do with it? I don't know. Let's do something similar. Let's take second. And then we'll divide it by the Planck time, because that's like a minimal unit of time. We're already doing that with its length. Why the heck not? Planck time. Oh, and I think we need to divide this. Oh, that's a very interesting thing right there. Now, I'm not going to comment on that, but that's not what I was looking for. Wait a second. This number here, this looks a little familiar. Why do I say this? It's 1.11 times 10 to the minus 17 seconds. Wait a second, didn't it look something like this guy over here? Wait a second, that's 1 over the speed of light squared. 1.11 times 10 to the minus 17. Now it has units here. That's second squared per meter squared, whatever that is, aka kilograms per joule. That's our equals MC conversion factor. That's like the magnitude of the mass and the energy you'll get out. I think that was correct. All right. Why is it the same thing? Wait a sec. I'm just trying to figure out how long hypothetically it would take to get something ridiculously small, essentially zero, but not quite, to within the speed of light. How long would it take to get that far? And it's like, I don't know, like a bit. Hold on, go back again. It's like it's every 9 of a billion. Uh, a little less than a billion seconds, or about a billion years. That's that's about all. It's our average Gregorian is. Hi, Kelly. Uh, what? Oh, that's interesting. Oh, that reminds me, because I looked at this and then I got really excited, and then I ADD'd out and started watching isn't it Angelina Collider video or something like that. I don't know. She has a degree in physics and she makes stuff and things. And all of a sudden we went into, hey, K-Shell, good to see you, my friend. Um, Basically, she started going to, what is it, the Kirchhoff's law and everything, going into the ultraviolet catastrophe and everything. So I had to play with that too. And our friend the Circle may make an appearance. We'll get to that in just a moment. All right. So where are we at right now? Oh, okay. So we got this thingy here. Let's go back forward. Go forward. Okay. So we get this magnitude out here. It said that's basically the relativistic mass of 1 joule. Why is it coming out in seconds? Why are we getting this magnitude here? It's well, okay. Well, here's the interesting thing about that, Kali. Um, Again, I don't have a full-fledged background in this, but I'm just like, well. To be fair, that's kind of close. It's not quite the magnitude of the Higgs boson's mass divided by the Planck mass. It's in the magnitude. It's not precisely it, because like if we take this and we square it, we get to greater than 1.05 times 10 to the minus 34. I'm gonna get slightly, I think 1.2 or something like that. Yeah, 1.23. So maybe there's a connection. It's within, what's the zeta? I don't know. I didn't find enough stuff there for to have me justify that. But the interesting thing is, if there is something about the unit of action going on, maybe this is why things are lined up the way they are, because it needs to be either perfectly in tune or within a very particular span. It's kind of reminds me of music. Uh, oh, Fibonacci Day, happy! Oh my God, wait, which one is Fibonacci Day? Fibonacci Day. 1 point. Sunday, November 23rd. Ah, okay. Why is it? Because it's 11 Oh, one, one, two. Okay, I get it. I think so. That's Poindexter. We are just talking about Keishel's Keishel's birthday is on Fibonacci Day. Happy post and pre-birthday. Okay. Where we at? Ah, yes. Oh, we're talking about 1 over c squared and how it's just like 1 times 10 to the minus 17 number over there. The speed of light. The speed of lice. Oh my God. That's don't get me on that. If you don't want a bed bug infestation, those things. Get the number 34, 20. I don't know. That was poison. Long stories. Uh, but ultimately, okay, we get this number of magnitude that's 1 over the speed of light squared. Cool. So that's our energy conversion factor of E equals mc squared. Yes. Wow. I didn't even think about that sequence. I just uttered the words because it was a script in my mind. I'm sure large language models hadn't noticed that. Um, okay. So we get that number. Okay. Where did we originally get that number from? Well, originally let's conjecture. If we were to assume that our dimensions, time, space, mass, charge, and temperature, are going to be in balance, we have 5 Planckian bounds that correspond to those. Coincidentally, from those 5-dimensional ingredients, you can construct the constants of nature. Now, it might be a weird combination of those, but you can do it with just 5 base elements. That's an interesting thing I don't hear enough about. Also, from all the constants of nature, you never have more than 4 of them being expressed. Now, you might have them in different powers, like big G is it? It's length cubed because it's talking about a volume thing, and it's divided by mass, and then seconds squared because it's an accelerating thing. So you might have them to different powers. You're never going to find more than 4 expressed at any one time, which is also an interesting thing. Sounds a little orthogonal to me, but hey, what do I know? All right, so where we're starting. So what if we took our literal ones of the base building blocks of reality and we set them equal to their dimensional ones? Because that's how we're literally defining it. All right. And since we want a unit to come out, we're going to need a 1 squared to get that other dimension. Otherwise, a length divided by a length is just going to be a number relationship. It's going to be a ratio. We want our dimensions. Why? Because Wolfram Alpha can do it, so it makes it a lot easier for us. But all right. So again, we're going to conjecture. What if the minimal possible length? Its dimensional inverse in its same dimension, aka we take meter squared and we divide by the Planck length, gives us the radius of what we would colloquially refer to as universe. Or for a realm of persistence, because if you're going to say something is finite, and by definition, big U universe is all things, we're going to say little u universe. I know it's weird, and different stuff means to like astronomers, it means the observable stuff, and the cosmologists are like, no, we got to talk about the whole dang thing. Why? Because cosmologists. Hey, listen. It ain't my job. It's a lot of smart folks. Professor Keating, Professor Carroll. There's a lot of smart folks off them. I would give additional credence to what they say because it's their jobs. All right. So again, we have a conjectured radius of the universe here. Okay, what the heck does that mean? We're almost about 100 million times larger than the diameter of the observable universe there, about 93 billion light years. All right. So what are we doing to this? Well, we're like, all right, if we were to take our concordance model, we either start at whether it was a singularity or a very hot, dense state, a primordial atom, if you would. How long would it take for it to reach that state going at the speed of light? Take approximately this long. About, it's going to take about a billion years. Wait, it's like a billion. That's greater than the 13.8 billion years. That's 100 million times greater. You crazy person. We can't be that old because that give us a lot more chance to have stellar nucleation, and galaxies would have been around for a long time and may help explain why the James Webb is seeing very old, mature galaxies as we look farther and farther back. I'm I'm just saying, listen, these are just some numbers. You don't have to give credence to them. But I'm just like, hypothetically, if there was something to this, might it help explain other things? Because here's the thing. Ultimately, this is all numerology. Numerology is numerology until it explains more with less. So that's my claim there. Can we explain more with less? Like, we don't need to put in all these inputs, or we're looking at the data and we're trying to fit the data, and we're looking at that, and the data is telling us, well, it kind of looks this way. It could be wrong. Our data could be wrong, but I'm going to assume that the vast majority of data, at least to a certain precision, is right. Okay. And we get new information out there, and we're completely wrong, then we're completely wrong. But for now, we're going to attempt to do science, which science isn't a person, science is a process. I think that's really why it's really cool. All right. So we have this thing. All right. So it's saying, wait a second, hypothetically, our universe, and that's only to get to that part. Are we at that level? Are we around that spot? Have we been at that spot for a while? I don't know. Well, ultimately, that is the correct question. Is that the right question? Is the question right? So I feel like people have been arguing about that for literally thousands of years. And I think, like a lot of those folks, I don't have an answer either. The question, well, it it, it is claimed that when Professor Einstein was asked at one point, Professor, it's like, you need to solve, if you were presented a problem and told you need to solve this in 1 hour or the world would be destroyed, how would you go about it? He paused, he said, I would spend 55 minutes precisely crafting the proper question and spend 5 minutes answering it. I have no idea if that's a true statement, but at the time, I'm just like, I mean, that seems like the right way to go about it, because you could be like, I have the answer, I have the answer. Or you just start saying, this is the thing, this is the thing. Maybe that's the thing. Is that the proper thing for the current stuff that we're talking about? Maybe it is. Maybe it isn't. Some folks may have experience saying this is the way it will work. Maybe circumstances are different. I feel like we're getting into category, group, set theory, and stuff. And this is why I say mathematics solves so much of the BS and everything. Why? Because if you actually just start going by, well, this happens. If we can account for enough variables, maybe we can make better decisions. Hey, I don't know. Oh, thank you for listening to my ramble. All right. So if we're gonna say it take approximately that long, going at the speed of, like, the maximum speed according to physics as we know it, it would take about a billion years for it to get to that size. Because they can claim the solution is contained within the problem. I mean, that sounds right. That sounds right. I mean, that would be poetic justice, wouldn't it? It's wouldn't that be it all? Um, all right. So what was I doing? Oh yeah, this whole conversion thing. All right. And then we're just relating it to my time. I'm like, wait a second. I get this in seconds, and then we could always just do this and forget if I have a habit of playing, being like, oh, I need to share this with the class. I need to share this with the class. And then all of a sudden I'll do something else. Okay. As we can see, we get this ratio, which is essentially at 1 over, and then we can always just do take a joule divided by c squared. So we're getting the energy out, and we're getting its relativistic mass. We want it with more digits. So yeah, basically we get this. We get this 1.126 times 10, and then that would be minus 17 kilograms within kilograms, aka the relativistic mass equivalent of 1 joule. What what is the magnitude of 1 joule doing doing in these calculations? I mean, I'm sure it's just built in. Um, I mean, that's what it really seems like to me. Okay. Um, that was the main thing that I really included there. That I was going out for a run last night. I'm like, wait a second, what do I do with this? I'm like, oh, well, it's one of those questions you have, and you're like, okay, I could just do that. I'll go around to that. Oh, it's a simple thing. You need to run a quick thing. You're like, oh, I wonder where that goes. Okay. So now, my friends, we can go to another place. Oh, wait, I should probably actually write this on the board. What do we have? We have. Okay. All right. I need to remember what the heck I was talking about. What happens when you go on like 6 different tangents. All right. So we had that. Yeah, that magnitude. So what do we have? We had okay. So we're gonna say, God, it's such a crazy thing to conjecture. RU, so the R of radius of universe, so to speak, we're gonna claim is meters squared over length. Okay. That equals x times 10 to the 34 meters. All right, ginormous. All right, so we've got that, and then if we do our u divided by c, and then we divide by crazy. We do times, so we're doing uh seconds. We'll do that squared, like the other code, over LP. That equals the magnitude of 1 joule, which is equal to the magnitude of 1 over c squared. Okay. Well, WTF, mate? What's going on? Does that actually kind of come on? Okay, it actually kind of, hold on. Let me biggen my screen a little bit. Let's do a little bit more. All right. All right. So it actually kind of comes out if we actually have it a decent size. Okay. The whole point is, all right, we've got C, the speed of light in the vacuum, even though there's no true vacuum. All right. We got C squared. What's it give us? It gives us this really large number over here, almost 9 times 10 to the 16 meters per second, all that squared. Okay. And then if we happen to do 1 over c squared, we get this number right here. We get 1.1126 times. What the? But actually put the times in there. Otherwise, that. Yes, yes. These are the things. Every once in a while, somebody makes a mistake. I'm like, I can copy it completely. And then, I'm like, no, no. It's like when you're doing a homework assignment, it's like, there doesn't seem to be an answer. And do you just brute force, you find an answer and you go to class the next day and the professor's like, yeah, there was no answer to that, so it's okay. It's also a different problem. You know what? I was up all night crafting a solution to it. It's okay. I digress. All right, so you get the magnitude over here, and then that's second squared over meter squared. Okay. You got that. I'm like, all right, well, let's conjecture. We got quote unquote radius of small u universe. Okay. What are we claiming that is? Well, if we've got boundaries here, oh, let's just do, we're playing around with units. Let's square meters and we'll divide it by the Planck rate. So that'll give us the dimension of length out. And we get about 6 times 10 to the 34 meters. That's a really large number. Okay. And then if we take this here, then all of a sudden, well, we can actually rewrite this. Let's rewrite this. Turn this into a tasty sandwich. How do we turn this into a tasty sandwich? We go, let's just take RU. That's meters squared over the Planck length. Oh, we're bracketing everybody up. Wait a second. So what you're saying is the connection between meters squared divided by the Planck length and seconds squared divided. Oh, hold on. Planck time. dp. There we go. Pardon. See, I'm making all these mistakes. All right. So what you're saying is meters squared divided by the Planck length divided by the speed of light and then divided by seconds squared divided by the Planck time is equal to the magnitude of 1 joule, which is equal to the magnitude of 1 over c squared. I thought that was pretty neat. And again, I'm sure the folks have noticed that in everything before, but it's like, all right, I see these things, and then we try to make sense about it. And I think that's about all for that portion. In RU, what does a meter square mean? How many meters? Blah, blah, blah. RU. Oh, just one. Sorry. It's 1 meter. Okay, to be fair, it should be 1 meter squared. There we go. No, I'm sorry. I'm used to, because when you do that, you end up it's like 6.1. Hold on, it's this guy right here. This guy. 6.187 times 10 to the 34 meters. Yeah, a very big number. That's the meters. Okay. All right. So finished that guy. Wait a second. Was there more that I had over here? No, we need to get into the Kirchhoff stuff. Okay. Oh. Where is it? It's wow, I cannot spell. No, it's the other one. Hold on. I need to go back to the way my mind keeps track of things. Hold on. Legal Danish. Oh my god. I am minus these. Wow. So many dang tabs. Okay, let's just do this. Hold on. Yeah. We'll do this and then do a video. Abby. Okay, so it's gonna be looking for this person. Angela Collier. There we go. That's who it was. All right, so we'll do this. Present. Share. Boom. All right, don't worry. We only need
is used to describe how much radiation you can see in the equation. For shorter wavelengths, this is going to go to infinity. And this equation is used to describe how much radiation
what is it
that's
again?
dependent on its objects. Heard of this one? So in the 1800s, people realized that objects emit radiation with a range of frequencies that's dependent on its temperature. To model this behavior, which was observed, the first approximation was the Rayleigh-Jeans approximation.
The Rayleigh-Jeans law. There we go. Something like denim. It's really. I totally spelled it wrong. There we go. All right. All right, let's look at our friend the Riley Jeans law. Okay. Now note. Oh wait, I'm not even sharing it with. Here we go. Here with class. Here we go. Riley Jeans law. As we can see, note there's no pi in there. Okay, the picture she was showing had pi, and that was tied to the calculations. I believe this essentially, as far as I understand it, you have this thing. It seemed to work with your different wavelengths and everything, and then Planck gets to it, and it's like you used heuristics with the math to get it to work, aka he played around until it worked. So basically, you can write it in different ways. Blah 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 blah. Then we get over to I think it's right around here. There we go. All right. No, it was right after. There we go. All right. So this is the one that we're using. So this whole thing is basically 2 pi times the speed of light times Boltzmann's constant times your temperature, and then you got wavelength to the 4th power. Okay. So I saw these and I'm like, I haven't computed this stuff yet. Let me look at it. So we did some stuff. Okay. Where should we start? Oh, we'll just put it in. Okay. We've got our Joule C squared there. So the thingy that we want, pop this out. All right, so I can actually read what it is. All right, so we got our 2 pi, we got our C, we got our Boltzmann constant there. T, since I'm lazy, let's throw in another one. All right, so the Planck temperature. Because if you're going to have a maximum of something, let's set the bound of the arena. All right, and then length. Yes, because I'm also a very lazy person. The Planck length or a wavelength. So it's a factor of the 4th power. All right. What do we get? We get this ridiculously ginormous number. That doesn't mean a thing to me. 5.4 times 10 to the 157 kilograms per meter seconds to the third. Pascals per second. All right, so it's pressure per second. Okay. It's a power density. Yes, more power. Yes, my inner Tim Allen is coming out. Yeah. Oh God, we broke off from alpha. What shall we do? Oh, geez. Hold on. All right, thank you. All right. Oh, that would have been a calamity. All right, so I got this thing, and again, I have no idea what this number means. I'm like, the heck can I do with this? Well, let me maybe I divide it by the biggest Planck number that I know. What number is that? Oh, it happens to be the Planck intensity. Like 10 to the 122 magnitude. So I'm like, that's the closest thing I know. What do we get? Okay. Looks kind of looks a little bit more than like 2 Planck lengths and reciprocal meters. Okay, I don't know what that is. Well, maybe if I just multiply it, I don't know. Is that going to do something? No, no, I can't even square this because I'm going to get half a length. What if, I had divided this into it? I'm just saying, what if hypothetically you just divide? I don't know. Is something interesting going to happen? Oh, look. Oh, you get off like, oh, that looks like about 2 Planck lengths. Oh, yeah. Oh, 2 pi Planck lengths. Okay, what is that? So we need to. Do I need 2 pi? Is that what it's telling me? That's it. Do I need like a circle to make this work? Of course, I need a circle to make this work. I mean, we are talking about wavelengths, so that had to come up at some point. Oh, listen, no comment. I'll leave it. I'll leave it at that. Okay. So I see this and I'm like, okay. So what if does this have a relationship to anything else? Let me oh, instead of the Planck intensity, let's play. What if we did, I don't know, what's below the Planck intensity? The Planck pressure, that's 110 to the 113 pascals. Why? Because, well, that's what it is. Under pressure. Oh yeah, it's that ginormous number right there. All right. Let's see what happens. Let's divide it by the Planck pressure. Wait a second. That number looks kind of familiar. It looks to be about 2 pi the Planck frequency. What? What's going on here? What did we oh wait, do we need our 2 pi there too? Do we need another circle to bring us all around? You do the hokey pokey and you bring yourself around. That's what pi's all about. Boom. Okay, yeah, so it is 2 pi Planck frequency to get that to a 2 pi Planck pressure to get to the Planck frequency. I mean, that's a kind of cool thing. Um, okay, and then let's see what happens. Okay. And again, there's an odd thing there, so unless we want to get really funky with our dimensional stuff. Okay, that seemed to get a little weird there. Okay. Now let's divide it. Why? Because we can. Oh look, we get the Planck time. That's interesting. Wait. So a 2 pi Planck pressure divided by this whole dang thing. Because, well, of course it's going to give us the Planck time out because we were getting the frequency before. Oh, okay, yeah. All right. How about we need something else? What's below the Planck pressure? Well, the Planck pressure is density times c squared. All right, well, let's divide it by the Planck density. Are we going to notice something else? Okay. We're getting buoyancy flux. So that's precariously close to around the magnitude. Is it is that 2 pi for the estimated amount of mass in universe, or at least the claim there? Is that 2 pi? No, it's not quite. Do I need to divide it by 2 pi? Is that what's going on here? See. I haven't played through all of this, so full disclosure. Okay. So how about rather than that, let's multiply it. Let's be brave. I don't know what any of that stuff means. Okay, let's divide it into this. Do we get anything neat? Okay. 9.5 times 10 to the minus 62 grams per volt amp. I don't know what that means. Okay. So we'll give up on this. We'll give up on our density. Are there any other units that might lead to interesting results? Hypothetically, let's check the Planck. Let's check out the Planck power because we can. We'll divide it in there. What do we get? God, 10 to the 105 reciprocal cubic meters. That's a number. I don't know what that is. I don't know what that is. Well, maybe if I multiply, it'll give me something friendlier. Does it give me anything friendlier? Nope. So I guess we're just going to have to divide this crazy number into the Planck power. Does anything interesting happen? Oh. That's kind of in the magnitude of the Planck volume. Wait, how much is it up? About 1/6? Let me take a crazy guess. So we need a circle. Well, apparently we needed a circle. To come full circle, what do we get? Oh, we get the Planck volume. Okay. I'm detecting a slight pattern here. Again, can't quite say what might be going on. So it's like, all right, we've got that. Have I done anything else with this? Okay. Well, what's the Planck power is like, let's check, it's about 10 to the 52 power. There we go. We can spell. All right. See, 5 over big G. Yes. Ah, 10 to the 52 watts. That's a lot of power. You can even represent it with logs because logs are useful, I claim. All right. Okay, what's below that? Let's do, how about the Planck force? Let's see, 4 over big G. 10 to the 44 newtons. All right, well, let's play, shall we? All right, we shall. So let's take, God, I don't even know if I'm, okay, I'm sharing the right stuff. All right, let's go from that. How about employ the Planck force? Why? Because we can. Planck force. There we go. All right. Let's divide it into that thingy. What do we get? Oh, that flux. That looks to be about the magnitude of the Planck pressure. Because that seems to be pretty close to maybe its inverse. I wonder what would happen if we multiplied it by it. Because it's under pressure. Oh, that didn't work well at all. Let's divide it. Oh, look, we got two-dimensional bound state momentum space wave function. I don't know what to think of that. Sounds like some Euclidean place with maybe a projection. All right, so instead of going through that, let's just do this. Take this whole thing, and we'll divide it into the Planck pressure. Under pressure. Oh, I wasn't expecting this. Kilogram meters per second? That's, wait a second, Newton seconds? That's momentum. Wait a second. That's such a weird number. What if I made the totally unreasonable expectation that I need another circle for this? What do we get? We had our 2 pi factor. Oh wow, it's thinking a lot. All right, reset. 5.6, excuse me, 6.52 kilograms meters per second. Looks a little familiar. That was momentum, right? I know, like a broken record. Like momentum. Wait a second. 6.52. 6.52 kilograms meters seconds. Oh, we get the Planck momentum when we set it up that way. I mean, it seems very interesting. It seems, and I don't know, it's just reality. It happens to line up. It's our reality. But listen, I'm just saying that XX misses memes. He was an internationally certified board behavioral analyst. She totally thought I was pretty spectrumy. Or maybe she was just angry with me at the time. Um, it wasn't meant to be. It's a good thing. It was a Disney World. We found out, we never stopped arguing. It's okay. Some people aren't meant to be. C'est la vie. Okay. So we got that stuff there. All right. We're coming up on an hour. Is there anything else that I actually did with this? Well, let's play around with H bar. Why? Well, because we can. Okay. So let's do this one last thing. Okay, these are the things that I do to just keep myself entertained. Let's, what if we square it? Actually, no, we'll just multiply it first. Did we do that before? I don't even remember. Well, let's see what we got. Oh, of course I'm gonna lag it out because I have to keep moving. I'm so impatient. God, I mean, I wouldn't be able to do these things in like a lifetime. Let's even if we have the debt, okay, maybe you could do it at some point or another, but it's to do stuff like this now, like this is like literal wizardry to me. It's like, wait, what are you doing? How are you doing this? It's WTF, mate. It's literally like freaking magic. All right, so we got that. That's okay there. All right. Inverse carrier recombination coefficient. I don't think I've ever heard those words before. It sounds like a cool thing for a sci-fi fic. Oh, it's gonna be just the sixth in there. All right, so how about rather than all that crazy stuff, just take our standard crazy stuff. Oh, well, let's divide by the elementary unit of actions. We were talking about that. Okay, that doesn't give me anything useful. What if we multiply it by it? Yeah. 10 to the 191 cubic meter per second square. Okay, that's making my brain hurt right now. And then let's just put it over here. Let's divide the h bar because that's the thing. How many dimensions do we get out? We got the mass out. Huh. Let's kind of around like frequency-ish, something like that. All right. Let's. No, we won't. We won't break any other things. It's I just find it very interesting when all of a sudden you just start seeing certain magnitudes. And again, maybe it's just because I'm consciously aware of this now. I'm like, wait a second, if I just do 1 over b squared, its inverse happens to be. Oh, want the unit? Get our dimensions in there. All right. Yeah, we basically get this magnitude, this 10 to the minus 17, or kilograms per joule, which when you take 1 joule and then you divide it by c squared, you just happen to get off. Oh, look, it's the same magnitude. It's just a conversion for c square. Why? I mean, I can do crazy things and just be like, oh, let me set this equal to uh, a random hodgepodge of stuff. So let's do the square root of the Planck mass, and then times we'll solve for x kilograms, and well, I don't know. We need some curvature, so I don't know. Let's divide it by pi, and then well, we need to braid it over 3 dimensions. We'll divide it by 3. And we'll do that over there. And we got this number over here. And so we're solving for kilograms. And we just put kilograms there. And hypothetically, if we were solving, okay, well, let's solve this for divide by meters cubed. Why? Because we get solved for a volume. So we do it on that side. We got to divide it on the side by meters cubed. And then coincidentally, we put in the same 1 base units there. We get it's quadratic, so we get a bunch of things out there, or we got variables the same magnitude, but we're solving for kilograms meters squared. So now we can justify kilograms divided by meters. Excuse me, meters cubed. Because we're talking volume. Oh yeah, that's about the dark energy mass density. I don't know. All we did was we just set it equal to the volumetric measures. A joule divided by c squared. I just think it's pretty neat. So we got some links and stuff in the doobly doo. Hey, all those who are watching, feel free. If you'd like to support the Physics Monastery myself, there's links in the doobly doo. And if not, hey, just keep sciencing out there. Why? Never given up on humanity yet. I wouldn't count us out. We're pretty ingenuitous. Yeah. Ingenious, industrious, in ingenudustiest. I'm gonna stop talking right now. So take care of yourselves, everyone. Have a happy new year, and we'll catch you next time. Peace out. Oh, did I even end the stream? Oh no.